Good morning. Is everybody in good shape? Where's our Kingsport class? I don't see anybody over there. Okay. I see David. You're there, right? Hello. Maybe they'll come in, right? We'll have maybe some more over here too. It looks like it must just be Thursday. Thursday must be the new Friday. You know what I mean? You know how it is in your classes on Fridays? I don't know what's the deal with that. But anyway, this is still Thursday. All right. Well, today I do have a few things to tell you here at the beginning, some things you'll want to know about. You'll want to know about everything I say today, won't you? Okay, but here's some dates you'll want to know about. Okay. First off, on Tuesday, coming up Tuesday, what's Tuesday's date? The 16th, 15th or 16th? Which is it? Tuesday the 16th, right? All right, on Tuesday the 16th, we're going to have a little quiz here in class. The reason is I want to make sure you all are doing something for me, and that's studying that unit circle. So we're going to have a quiz. Whoops, yeah, I forgot to switch. They switched for me. Thank you. All right, so a quiz on the unit circle on Tuesday. Here's what it's going to be. Okay, it's just going to be on D2L. I have a blank unit circle. That's what I will give you, that blank unit circle. You are going to fill in for me those coordinates, the degree measures, and the radian measures around that circle. Okay, that means for, like our 0, 30 degree, 45 degree, 60 degree, 90 degree, and so on, those types of angles around. You all have looked at that thing by now, I hope. If you haven't, it's time. That's why we're having a quiz, so I'll make sure you're looking at it. Okay, you have the actual unit circle filled out on there, and you have a blank unit circle. You have a question?
Yes, you said fill in the coordinates, and what were the other two things?
Fill in the coordinates, the degree measures, and the radian measures. Okay, the coordinates, the degree measures, the radian measures. So I'm going to give you, a blank unit circle. This is a very rough draft here. It will have things on it like this. And it'll say like something degrees and then something, which means radians when there's no label. And so like for this one, you're going to put, this is what coordinates there?
That's 0 or 1, 0.
Okay, it's 1, 0, and it's 0 degrees, 0 radians. Down here, there will be another place though where it'll say something degrees, something radians, where it's wanting to note that now we're at 360 degrees, 2 pi radians, right? Still at the 1, 0, but after we make that revolution. We'll have, up here we'll have one. We'll have things like this, okay? Coordinates here, square root of 3 over 2, 1/2. The angle's 30 degrees. It's at pi over 6 radians, okay? There'll be blanks for those things. You have the blank unit circle. I'm just copying that exact same thing. So it's on D2L, what you'll have. I'll have one for you, for everybody on Tuesday. Okay, so on Tuesday, September 16th, we'll have a little quiz on the unit circle because I need to guarantee that you know that. Okay, that's why. Some of you, I've not been sure if you've been looking over it. Some of you, yes, I can tell, and it'll be no problem. Others of you need to take the time over the weekend and look over it a little bit, okay? Any questions about that? Yes?
I still don't understand how you get the coordinates, the square root of 3 over 2 and 1/2.
Okay, for your purpose now, you're going to memorize them, but at this point, right? But here's what we're saying, okay? We have them actually drawn out more like this. We're saying our x coordinate square root of 3 over 2. We're going out square root of 3 over 2 units. What is square root of 3 over 2? Approximately 0.866. Is that what it is? If you look it up on your, if you calculate it and get an approximation. It might be a little more than that. I was trying to think. 0.866 maybe. Square root of 3 over 2. See what that one is? 0.866. Okay. So, what's that? Well, I've seen it before, so I didn't just calculate that. So just so you know, I've seen it before, so I was putting it back in there. So square root of 3 over 2, we're going over that many units on the x-axis, and then we're going up to get to this point, half of a unit. Now remember, up to here is 1, So essentially we're going up 1/2. My scale is a little off, as you can tell, but we're actually finding the coordinates of that point. We're going over so far on X, up or down so far on Y to get to a point there. What's up?
If you forget one, you're host.
If you forget one, yeah, you're not going to forget, because all we're using here, okay, this one up here is going to be the reverse, because it's the 60° or pi/3 angle, right? And this one here is going to be your 45° angle. That's what we're noting off there, which is pi/4 is square root of 2/2, square root of 2/2. All right, so look here, what you've got. Look coming down through here. What we essentially have, let me pull this mic over here a minute. I need this thing. So I can maybe, yeah, you're seeing that 1, 2, 3 business? Yeah. Seeing 1, 2, 3? Okay, we've got 1, 2, 3. They're technically all square roots. So square root of 1/2, square root of 2/2, square root of 3/2. We just don't leave it square root of 1/2 because we know the square root of 1 is 1, right? Okay, then going up that way, 1, 2, 3. Do you see that? That's going to help you remember. Now, how do they relate to the other quadrants? Because we need to know those other quadrants as well. How do they relate?
It's the same numbers, but the positivity and negativity changes depending on what quadrant.
Right, they're going to be the mirror image. You've got the symmetry going on, so that now in the second quadrant, the x's will be negative and the y's will be positive because we're in the second quadrant. Does that help kind of give you something to look at there a little better? Something to think about when you're looking over this so that you can get them labeled, okay? Anything else about that? So just be ready for that on Tuesday. Let's see, I should probably hook this on. I may be walking some more today. I don't know if I can put that on this. Well, we'll just pick it up when we need it. How's that? Now, another date we need to know. Tuesday, September 23rd. That one's going to be our first test over Chapter 6. Okay? So that's what we'll be doing on Tuesday, September 23rd. All right. Did anybody notice, did your homework get opened up okay? I mean, the ones that are called suggested homework on My Math Lab, did anybody check that out? Maybe it's not opened up yet. Okay. I worked on it. It still says past due? Okay, I'll fix that because you don't have to do the homework part for a grade. The quizzes you have to do, you know, quiz 1, quiz 2. That's what I'm grading on there, but several people had said they wanted the homework open. I thought I got it open, but I must have set the date wrong, so I'll double check it. I thought I had that one. Sometimes it gets I don't know, it goes back to default or something. It's probably my mistake, though, somewhere. All right, so I'll fix that up so you can be studying some more through the use of that. Okay. Yes, you have a question?
Yeah, when you said there's Tuesday, is it here?
It will be here in class. I will give you a blank unit circle in class. Everybody will get one. Kingsport gets one. You all get one. Okay, everybody's going to get one. And you will turn it in before we leave class that day. Okay?
What about the quizzes on My Math?
Yeah, we're doing those too. Okay?
Tell us when
Those are all due on My Math Lab. Those are all due at the end of the semester. However, right now the first 4 are open, and they're all related to Chapter 6. We're probably not through all the way through where the 4th one is. Tell you what, we'll look them up here. Oh, yeah, I think I've got to go to that other browser now for this. I forgot about that. Let's look at them here and see. Some of you have already been working on these. So can you do all 4 of them yet? Does anybody want to tell me about that?
I tried doing the first one, my internet kept cutting out.
Okay, that's something I can't deal with, right? When your internet cuts out. Okay, see, they're all due December 7th. It tells you right here. Quizzes and tests. So quizzes right here. The first 4 is what's open right now. Let's go over here, actually. I know you can do quiz 1, quiz 2 so far. Quiz 3 is from section 6.3. We've done that, so you can do that part. Quiz 4 is from 6.4. You're about to be able to do all that, okay? So that's what the quizzes that we have on there from chapter 6 right now, going through 6.4, yes?
How many attempts do we have?
You have an infinite number of attempts, okay? However many you want. It takes the highest grade, correct. Yeah, it takes the highest grade. So is everybody familiar with what's going on here? They're under quizzes and tests, but it's a quiz. You tell it you're ready to start. Yeah, because we didn't get to really pull this up before. You have questions here. Okay, you fill in the answer. If you need something from over here, this is your little toolbar on the left. See the toolbar? So if I need something in a square root or a pi, I just click over there. I'm not saying that's the answer. It's not, but okay. Just so you can see, though, the toolbar. If you want to do a fraction, it helps you do that. So those things, okay? So use this little toolbar. There's more things here you can use that it pulls up for you, okay? So that'll be helpful to note also. Whenever you're finished, you submit the quiz, and it grades it for you. Anything else about that, about what's going on so far? All right, so we've got some dates down now. We're into the semester. Big come now. We've got a test scheduled, so we're in good shape, right? No, y'all didn't want that. Okay, so let's go back to what we were looking at last class. Last class, I'm trying to remember where we were. We were finishing up section 3, 6.3, and we started section 4. So in 6.3, we talked about the even-odd properties, if I'm recalling correctly. We discussed the even-odd properties for the trig functions. And then we went into 6.4 and started looking at the graphs of the sine and the cosine. I think we got the graphs of both of those plotted and up on the screen. We looked at their domain and ranges. We looked at, we kind of verified which one's even, which one's odd, that sort of thing. So we're going to look back at that a little bit today too. What about over on page 391? Did anybody have a question from 390? Yeah, I think it was 391. We added some problems about even odd with the negative angles. Did anybody have a question from that part? 85, and then I'll get yours back there, okay? 85 on 391. It says the sine of negative pi 12ths times the cosecant of 25 pi 12ths. First, let's make this angle positive. We said we could use our even-odd properties to do that. Is the sine function even or odd? It's odd. So which functions were even? We only had 2 that were even. Which ones? Cosine and secant, right? Cosine and secant are odd functions, so or even functions. Whoa, take that off the microphone there. All right, so cosine and secant are even functions. They're the only 2 even ones. The rest are odd. So when we have an odd function, instead of writing it with the negative angle, what can we do? Remember? It's the
negative sign?
Yeah, take the negative sign. So it's going to be the negative sign of pi 12ths. It's almost like we're pulling the negative out front. That's not really what we're doing, but that's what it appears to look like there. This cosecant of 25 pi 12ths, I don't know. I'm a little concerned about 25 pi 12ths because it is not saying pi 12ths like the other angle. Where is 25 pi 12ths?
It ends up being pi 12ths.
Okay, it ends up having the same trig function values as pi 12ths because we go around 2 and 1/12 pi, or 2 pi and pi 12ths more. Okay, so 2 pi is all the way around, and then pi 12ths more. So that this whole revolution here that I drew is 25 pi 12ths, the whole revolution plus the pi 12ths. And so we have the same trig function values as a pi 12ths angle. So the cosecant of 25 pi 12ths will be the same as the cosecant of pi 12ths because they have that same terminal side. They're ending up at the same place there. Now we have our angles the same. We have a sine times a cosecant. Sine and cosecant are reciprocals of each other. Okay, so what do we get here? Yeah, -1, because this part here, the reciprocals give us the 1, and the negative just comes down. So we get -1. So we changed our negative angle to positive, and then we looked at the fact that 25 pi 12ths, that angle would have the same trig function values as pi 12ths. Yes, go ahead.
Later in the class, are we going to get to where we find the ordered pairs for these pi 12s and these weird things, or is that something we're not?
Okay, so if we were finding the ordered pairs for a pi 12ths angle, we would be finding the cosine and sine, right? And we will eventually be finding those, not in this chapter, okay? But we will find those. We have some formulas, though. We have to use formulas to find those because they're not the ones that we just see. But the fact is, pi 12ths, we can get to that angle by taking like half of pi 6, okay? So there's a half angle formula we can use. We can add two angles together or actually subtract for this one and get this angle. And so we have some indifference formulas we can use. That's later on, though. So don't worry about that just yet. All right, you had a question back here. 87. Are we okay on 85? Everybody good with that one before I leave it? All right, 87 says the sine of -20 degrees over the cosine of 380 degrees plus the tangent of 200 degrees. So let's see what we've got here. First, let's make the negative angle positive. Same idea. Sine is an odd function, so that is the same as negative sine 20 degrees. Now we've got these other angles in here. Let's see how they relate to anything. 380 is pretty easy to see there, I guess, because we go 360 plus how many?
20.
Yeah, plus 20. So this part here is 20. Okay, so the 380 degree angle will have the same trig function values as the 20 degree angle. So cosine of 380 will be the same as the cosine of 20 degrees. Now that 200 degree angle, where's that one? It's 20 past 180, isn't it? So here's the 200 degree angle coming around this way in black. I labeled that one in black. We note that this little piece here is 20 degrees past 180, right? 20 degrees past 180. Okay, it's what negative? Be a little more clear with me.
20 degrees from, because it's in the third quadrant.
Okay, 20 degrees from 180, it's in the third quadrant, so what's negative? What's negative? The cosine's negative? Cosine's negative, and the sine's negative. And we're looking about the tangent there. So it'll be positive, right? The tangent will be positive, so we're getting some good thoughts going here. The tangent of a 200 degree angle will be positive. So let me ask you this. Let's write this up here. Tangent of 200 degrees equals something positive. We don't care what it is, but we know it's positive, right? How does that relate to the tangent of a 20 degree angle in the first quadrant? See how they're directly, they're corresponding, right? If one of them's 20 degrees past 180, the other one was 20 degrees past 0. What do we know about their sine and cosine values, or their x and y coordinates? They're mirrored, right? They're going to have the same coordinates, except in the first quadrant up here with the 20 degree angle, they're going to be positive, positive, And in the third quadrant, they're going to be negative x, negative y, right? So I think that's where you are kind of thinking about some of these ideas when you say something's negative, something's positive. Okay, so in both cases, they have the same numerical values, but they just have opposite signs on their coordinates. What does that mean about their tangents? They will be the same. The tangent of the 20-degree angle will be the same as the tangent of the 200-degree angle. They will both be positive. They will be the same. Are we together on that part? The tangent of 200 degrees is going to be the same as the tangent of 20 degrees. Do we see that? It's where they're mirrored down there, okay? They're corresponding angles. We have one that's 20 degrees up from the 0 degree angle. We have one that's 20 degrees below 180. They both end up having positive tangents, and because of their locations, they have the exact same tangents, the exact same values. So the tangent of 200 degrees is the same as the tangent of 20 degrees. So we want to replace that so that all of our angles are 20 degrees here. We've got them all in the same angular measure now. Questions so far? That part's a little, maybe the hardest part to see right there. What's that?
It's really cool though.
It's cool how it works, because this is why this part says don't use a calculator. They want you to think about where these things are and how the angles in the different quadrants are relating to each other, how the angles are related, and how their trig functions are related. Okay, that's what we're looking at. We don't really care what the tangent of 20 degrees actually is. We don't care about that. So that's probably a good thing right now. All right, so tangent of 20 degrees then we said was going to be positive. It's going to be the same. These two are going to be the same. Now what about what I'm working on up here, back on this line? What about that? Yeah, this is negative tangent 20 degrees, right? Because sine over cosine's tangent plus tangent 20 degrees gives me 0. A lot of work for nothing, right? A lot of work to get 0. That's what we're saying there, okay? A lot of work to get 0. But we're relating these angles. We're seeing where the 380-degree angle ends up at. We're seeing where that 200-degree angle is. We're relating some trig functions. We're still using our identities, our sine over cosine. A lot going on in this problem. This was a good one to look at. Any other questions on 87? Yes, go ahead.
I got 180, or 200 minus 20 degrees gave me 180 degrees, and that equals 0 still. Is that completely breaking all the rules?
200, no, wait a minute. Tell me this again.
Negative sine 20 over cosine 20. I kept the tangent 200 degrees, and then those ended up being tangent of negative 20, sine and cosine. So then I had negative tangent 20 degrees plus 200, the tangent 200, and I subtracted them, got 180, and then
Yeah, that
did the y
actually
over x.
does not normally work. So it was coincidental on this one, okay? So be careful with that. All right, we want to relate our angles, though, here, using the rules, the identities that we've looked at, okay? So that's what we're trying to do in this part. Anything else from this section 6.3, those problems? These were probably the toughest two on that part, I'm guessing. Anything else there? All right, let's go over where we started on 6.4. Trying to remember, over on page 403, I just asked you to look at 3 problems that talked about the general idea of the graphs, right? I think that's all we were looking at so far. Those were on page 403. All right, let's see, we were looking at number 3, 9, and 10. Did anyone have a question on 3, 9, or 10? We're going to go a little further in this section today. We want to see some more things here. Let me first kind of recap, and this would pretty much answer some of the questions that you're being asked on 3, 9, and 10 there. So if you didn't get those, go back and look at them. But we're in section 6.4. And we're looking at graphs of the sine and cosine functions here. Last time we did graph these, so I'm not going to go through the plotting of the values again unless you just really need me to. But here's what the sine graph ended up looking like. We said its range, I'm putting the range up first just because that's what I wrote first, is from -1 to 1. What was its domain?
Negative infinity to infinity.
Right, negative infinity to infinity, which means all real numbers. That's just another way of saying all real numbers. Okay. We had labeled some coordinates here, pi halves, pi, 3/2 pi, and 2 pi. And the sine graph, we said we would say this loosely, that we're starting it at 0, 0. Okay, it's starting at the origin. We're not really starting it. We know that's part of it, though. It comes down, whoops, halfway through the pi. I didn't draw it too well this morning. And comes up like this, illustrating one period of the graph. What was the period of the sine graph?
2 pi.
2 pi. And basically, what did that period mean for us?
It's like one complete revolution of the circle.
Right, it's like one complete revolution of the circle, and on our graph we see that's how far out this wave goes before it repeats itself. Okay, so that's another way of looking at the period, how far the graph goes before it repeats, because essentially what happens is it keeps on going in the same style, like that. Okay, it just continues on. We also looked at amplitude for the sine function. The amplitude here was what? 1. And the amplitude we said we're measuring from the middle of the graph up to a crest of the curve. So it was 1, or down to the crest of the curve. Either way, it's 1. So that's showing the amplitude there. What about X-Intercepts? I'm not sure we looked at that. Let's put that up here. Where are the X-Intercepts for this graph? Okay, so 0, pi, whoops, not pi over something, sorry. 0, pi, 2 pi. We've got a lot of them, don't we? We had some before 0 also. A way we can describe all of those, 0, pi, 2 pi, 3 pi, don't forget about it. We would have negative pi, negative 2 pi, all those. We're going to call those integral multiples of pi. Integral multiples of pi. Or you could illustrate, with the little dots on the ends there and show, we're going in this pattern, these things. Integral multiples, that means we're talking about integers being in front of pi. What are integers anyway? What are they?
Whole numbers.
Okay, whole numbers, and technically, and their opposites, okay? Whole numbers actually are just 0, 1, 2, 3, 4, and so on. But to include the negatives, that's where the integers comes in. Whole numbers and the opposites of those whole numbers. 0 doesn't have an opposite, but the others do. Those are your integers. So we're talking about integral multiples of pi, where we have our x-intercepts for our sine graph. Sine graph in general, the function is in this form. The form of a sine graph, or the form of the equation, is y equals a sine. Your book uses omega. It looks like a W when I draw it. It's a lowercase omega, Greek symbol there. So it's a lowercase omega. Some of you will say, well, that's just WX. What that omega value is representing, this right here, it's just the coefficient of x. It's whatever's out in front of x in the argument of the trig function. Remember, we call whatever we're taking the trig function of the argument. So if I'm doing the sine of 2 pi, then 2 pi is the argument of the trig function. The coefficient of the argument is what we're calling omega here. We also note we have an a out front. These things help tell us some things about the graph. So if we know the equation of the trig function here, an equation is given, then we know from that equation for sine that the amplitude will be the absolute value of whatever a is. What does absolute value mean?
It's like the negative, or it's your distance from 0.
It's your distance from 0. That's exactly right. So absolute value is telling you the distance from 0, and so therefore our amplitude is always positive. Now actually the period of the graph is always positive as well, even though they don't normally put the formula here in absolute value, but the period is always positive because it's telling us how far out the graph goes before it repeats. So that is just by definition, that makes sense for it to be positive. The period for a sine function will be 2 pi divided by omega. Now what's happening here is that we said the other day that the period of the sine graph, and we said right over here, is 2 pi. That's if we have y equals sine x. When we start putting other numbers in there, you know, we might have y equals 3 sine 4x. That's going to change the period of the graph. It's going to change the amplitude. The overall graph is still going to have the same shape as the general one we put up here. But things are going to change when we start putting other numbers in here. That would make sense, wouldn't it? If we start putting different values in, the shape's going to change. Well, the overall shape's the same, but how wide or how narrow or how tall, those things are going to change with our graph. We're going to see some of that today too. But because the basic period of the sine function is 2 pi, then we use 2 pi over omega, whatever that coefficient is, to get the period of whatever sine function we're working with here. Those are some things we'll want to know. Do we see those things up in our original function up here, y equals sine x? We should. When we had y equals sine x, what did we really have? Y equals 1 sine 1x. So the amplitude was 1. They're in the front. Those ones were understood. You know, in math, we like to say things are understood, whether they are or not. But those ones are understood. So we have 1 out front, indicating the amplitude. We have 1 in front of the x, so that when we do 2 pi divided by that 1, we get the period is 2 pi. That's our basic sine function that we were looking at up here right now. Anybody have a question so far on that? Go ahead.
Is your amplitude and your omega value, are those going to be the same? Because
amplitude and omega do not have to be the same.
Okay.
No. And we'll see some examples, okay? This same stuff holds for the cosine graph. Let's go ahead and refresh our minds on the cosine graph, and then we'll look at some where we actually have to decide the amplitude and the period. And we'll even sketch the graph, okay? See what those look like. So y equals cosine x. This was the other graph we looked at last time. Again, for the general cosine graph, the period is 2 pi. The amplitude was 1. The domain was still from negative infinity to positive infinity. And the range was still from negative 1 to 1. We'll check out what the x-intercepts are here in just a moment. So everything's pretty much the same, and we even noted, I think it was at the very end of class, we noted that the sine and cosine graphs look just alike. One of them's just been shifted over pi halves units. And we called those sinusoidal graphs. Remember that? Sinusoidal. Now, overall, this cosine graph, it starts up at 1, or up on the y-axis, not at the origin. It's not really starting there. We want to keep that in mind, even though I've used that term. It's coming down like this. It's going up like that. That's one period of the cosine graph right there. But again, whoops, as it goes on, it got worse when I drew it. But anyway, it continues on in that same pattern. Sometime you'll want to look at one either on the internet or from the textbook where it looks a little better. Remember, if you graph these on a graphing calculator, you want it to be in radians. So put your graphing calculator in radians if you're trying to do this on there. No, we're still not using a calculator on the quiz or the test, okay? Just in case anybody's wondering, we're still not using one. But just so you can see a better picture, you might want to look at it in the book or on your calculator. My drawings are pretty bad up here. All right, x-intercepts. X-intercepts are where on this one? You see them? Pi halves, 3 pi halves. What's this one back here?
Negative pi halves.
That would be negative pi halves, right? Again, they keep on going because the graph continues infinitely. So do the x-intercepts. We might label these at, what kind of multiples can we call this? What would the next one be after 3 pi halves? 5 pi halves. So I'm going to call these odd multiples of pi halves. How's that? Odd multiples of pi halves. 1/2 pi, 3/2 pi, 5/2 pi, negative 1/2 pi. Does that make sense? They're odd multiples of pi halves. So just to kind of summarize what we're looking at there. All right, so general form, still y equals a cosine omega x. It looks just like the form for the sine function, doesn't it? Same thing. Amplitude, still going to be the absolute value of a, period, still going to be 2 pi over omega. Sine and cosine graphs work very similarly. Are we okay so far here? So far I'm giving you information about this stuff. Some of it's repeating what we said on Tuesday, just to get it back in your head. So we've got a better grasp on it hopefully today. We're going to look at some equations. We're going to see how to sketch a graph. I always like to say sketch a graph because everything I do up here on the screen, it's definitely a sketch. Okay, so I expect you all will be sketching as well when you take notes. Let me get one out of the textbook here for us to look at and see what we've got. Let's start out with one. I'm going to use number 12 out of the book on page 404. Let me hold up just a minute. Some of you are still writing here, so any questions on what's up here?
On the period, the 2 pi over omega, I get that we're not putting in the omega before because it was always 1. I'm just wondering where we're getting that value from.
Where we're getting the omega value from?
Yes.
Okay, the omega value is, okay, I'm going back up to the upper left corner here. The omega value is sitting in front of the x. It's understood here to be a 1. That's where it's coming from on this. It's always the coefficient of x in the argument of the trig function. I think you'll see it a little better when we look here at one that has an actual numerical value besides 1 there. So let's see if that helps, okay? Anything else so far before I leave this screen? Okay. Well, number 12 doesn't have something besides 1, but we'll still go with 12 since I said that, and then we'll go to a different one, okay? 12 on 404 says y equals 3 cosine x. In these exercises in the textbook, they just ask you to find the amplitude and the period of the graph, and they tell you you don't have to graph it. We're going to graph it, though, because you don't have to graph it when you go in the textbook and do this, but there's others in there they're going to ask you to graph, so you need to know how to sketch the graph. All right, so remember, I'm going to write over here y equals a cosine omega x, and I'll put back up here the amplitude is the absolute value of a. The period is 2 pi over omega. I'm using some abbreviations here. You all got my abbreviations down? All right, we're good on that? Okay, so what is the amplitude in what we're looking at?
Absolute value of 3.
Yeah, absolute value of 3, which is just 3, right? Amplitude, everybody's going to get the amplitude right on every one of these. That's pretty easy to see, right? Amplitude's good. Period, that one's a little tougher normally, maybe not in this particular case, but the period here is 2 pi over 1. Omega is 1 again, it's right there in front of the x. So the period here is still 2 pi. What changes when I sketch the graph? The amplitude. So what do I need to do on my graph? Okay, on the y-axis, I'm going to be up at 3, down at negative 3. So I need to make sure I'm showing, it's going up to 3, down to negative 3. Now, when I'm graphing these and I see whatever the period is, the period here is 2 pi. So I know I'm going to go out 2 pi units before I repeat. The other important thing to label on my graph when I'm going to do a sketch is where is halfway through that period. Halfway through is at pi. Why am I interested in that? Well, if it's a sine function, it's going to cross through the halfway through point. If it's a cosine function, that's where we have a curve, remember. Let me go back a screen. I'll come back, so don't think I'm leaving this totally yet. If it's a cosine graph, remember when we did just the one period of the function here? Halfway through is where we have that curve right there on the cosine graph. Halfway through on the sine graph is where we cross through the x-axis at pi. So it's important to know what's halfway through. You might even want to label those half of halfways so that you can see, like here, where the curves are. I usually don't on mine, I'll be honest, but you might want to, because a fourth of the way is where you're cutting through on those x-intercepts on the cosine graph, or where you have the curves on the sine graph. All right, so what we're going to do over here is sketching the graph. I look up here and I see it's a cosine graph. So where will I start?
You'll start on the 3 on the y-axis.
Okay, so for my sketching purposes, I'm going to start up here on the y-axis at 3. I'm going to come down like a cosine graph, go up, and then I can show, you know, that it goes on. I can extend it on both sides and show that it continues on in those types of directions. Just have an overall graph here. Okay. This part said you didn't have to graph. Later on, they have you match up some graphs with some equations, and then they have you show at least 2 cycles. I didn't show 2 cycles here completely, but as long as you can get the general idea of what the graph's looking like, you would be okay there. Now, let me ask you on this one. What's the domain? That would be the range. Negative 3 to 3 would be the range, right? Negative infinity to infinity is still the domain. Our x's are still being covered by all real numbers. The domain, though, has changed. That y scale has changed from negative 3 to 3. So the range has changed. Any questions on this one, on the cosine graph here? All right, so to make life a little more interesting, let's put some fractions in our equation. Still on page 404, this is number 18. Y equals 4/3 sine 2/3 x. All right, so we need to first figure out what's the amplitude. 4/3. See, everybody's got that now. Period is going to be 2 pi over what? 2/3. So let's note here, the amplitude, the a value, and the omega are not the same. As we said, they do not have to be the same. They weren't in the other problem either. I just didn't point that out. But in the last problem, one was 3 and one was 1. Here we have a 4/3 and a 2/3. The period is 2 pi over 2/3. So what do we say the period is? I don't like how that looks. We never leave it like that. What is it?
6 pi.
Okay, I hear 6 pi. I heard 3 pi. Anybody else?
It's 3 pi.
3 pi. 6 pi over 2, which is 3 pi, right? It's 3 pi. How did we get 3 pi? This is 2 pi divided by 2/3, which means times 3/2. This is 2 pi over 1. Those 2's cancel, okay? Or as you said, you get 6 pi over 2, giving us 3 pi there. When we had 2 pi over 2/3, that's what we call a complex fraction. We have a fraction inside of a fraction. They look pretty ugly. We don't like the looks of them. We always simplify those out, okay? So we want it to say 3 pi instead of 2 pi over 2/3. So be careful with those fractions. We're going to multiply by the reciprocal of what's in the denominator to get the 3 pi. Well, let's sketch the graph. This time on my y-axis, I need to show what? Yeah, up to 4/3. Hey, it basically looks like the last one I drew, except I'm changing the numbers I'm putting up here, right? I'm going up to 4/3 this time and down to negative 4/3. That's what I'm illustrating here. It's a sketch. I'm illustrating where that period will go or how far up those curves will go. The period goes out to 3 pi. Again, it looks the same, but now this is 3 pi that I'm using. Halfway to 3 pi. What's halfway to 3 pi? I want to mark that one also. What is it? 1.5 pi. Is that what you said? 1.5 pi, right? So how do I write that up here? 3/2 pi, right? 3 pi divided by 2. 3/2 pi. I notice I have a sine function this time. That tells me how to sketch in my graph. Where am I starting? At the origin. So I'm here, going up to there, down through, up there, and I could continue on in that pattern, okay? But that gives me my overall idea of what the sketch is going to look like, the sketch for this graph. Domain is still negative infinity to positive infinity. The range this time is from negative 4/3 to positive 4/3. Question on this one?
If you're going to draw this out as a circle, I'm trying to like conceptualize the omega, because what I'm thinking about it is that that would be like how far along the x-axis you go, and if it's a circle, it should be the same as how far along the y-axis you go.
What do you mean draw this out as a circle?
Like,
Are you talking something about the unit circle, using that?
well, yeah, but it wouldn't be the same values as a unit circle because you got the 4/3 for the y, and then the omega value, like.
Okay, maybe we should just say here, okay, before you go further, whenever we are graphing this equation up here, okay, it's not going to be a circle. We would just want to see that as a wave, okay? Because if I were going to graph something that actually looked like a circle at this point, I would be graphing something in the form, x squared plus y squared equals r squared, where I could get circle coordinates. I think you may be relating it a little bit to maybe you've worked with polar coordinates before. Yeah. Have you worked with that? Let's hold off on that for now, okay? All right. When we graph this, we want to see that sine wave, okay, or the cosine wave. That's what we're looking at here. Okay, let's look at another question about one like this, and then we will look at some of the other graphs and see the overall shapes of what they're going to look like. Sine and cosines look a lot like each other, though. Let's look at, this is number 46. I'm skipping over pretty far now on page 405. 46 is y equals -4 sine 1/8 x. They have some graphs in here and some equations that they want you to match the graph with the equation, and I'm going to ask you to look at those. I'm not doing any of those right now in class, but still on those equations, you'll want to know what the amplitude and period is in order to match up with the graphs that they've already drawn. You'll have to kind of compare to their scales. What's the amplitude here? 4. Good. What's the period here? Okay, I'm going to give everybody just a minute to figure out and make sure what they think the period is, okay? So what's the period? 16 pi, right? Everybody get 16 pi? 2 pi times the reciprocal of 1/8, which is 8/1, will be 16 pi. Okay, remember it's 2 pi over 1 up there on top, and then times the reciprocal of that denominator. You know, we've been having a lot shorter periods on these graphs, so this time it's out to 16 pi. Halfway through we'll be at 8 pi. We're going up to 4, down to negative 4. What this is going to do, if the period of the graph is 16 pi, it's going to really spread out those waves, isn't it? I mean, if we were looking at that, it's really stretching those waves out a lot more than when the period was 2 pi. What else do we notice about this equation? What about that negative in front of the 4? What's that going to do to anything? Okay, so start at negative 4, flip the graph. It's reflecting it over the x-axis. So when the equation starts with a negative up there, we do have to note that something's going to change there. It's going to reflect the graph over that over that x-axis. I keep saying the wrong coordinate today. Over the x-axis. So we're going to essentially start. Well, we don't really start at negative 4 because what kind of graph do we have? It's a sine. So we still start where? At the origin. But that means we're going down instead of up, right? We're going down instead of up because we've reflected it over. So it's got to come down here. It's got to cross through there. It's going up and curving at 4 up on the y-axis and something like this. So that's showing basically one period of the graph. This one's very stretched out. Everybody okay on sketching the graph, finding the amplitude and period? All right, so if we're okay on that, let's go backwards then. You know, we like to do things forwards and then backwards, so we're going to be backwards now. I don't want you to face the back of the room. Don't do that. All right, the backwards thing. Here's the backwards thing. Now I'm going to give you the graph, and we're going to write the equation. All right? So far, I've been giving you the equation. We've found the graph. So now I'm going to give you the graph. Let me find one here that I'm going to give you. I'll give you number 64. So that if you've got your textbook, you can look at that on page 405. If not, though, I'm going to try to duplicate it up here. We have something looking like this on the textbook. This says 2 pi, and then we've got that. And then we've got 6 pi labeled. Then we've got 10 pi. Back here we have negative 2 pi. Negative 4 pi. Up here we've got a 4. Down here we have a negative 4. And then we've got a graph that looks like this. This is the part, let's see how well I can draw it in. Oh, already messed up. Whoa. The pen is getting a mind of its own here. All right, that looks pretty bad. The book looked a whole lot better. All right, I think we can get what we need from this. Maybe. We want to write the equation. I want to say write an equation because remember we said these graphs are sinusoidal, so technically we can write one in terms of the other. When we were talking a while ago about reflecting that other graph over the x-axis, you all may remember doing other transformations on other graphs in the past where you did vertical or horizontal shifts. Remember vertical and horizontal shifts? So if we were to do a horizontal shift, we could write this as another trig function. But the easiest trig function to write this one in terms of will be what? What does it look like? More like a sine or cosine? It looks like a sine graph, right? So we want to write it the easiest way possible. So we're going to use y equals a sine omega x. That's our form that we're using. What is the amplitude for this graph? 4. You got that by just looking at the graph and seeing that it goes up to 4, down to negative 4, correct? You see the amplitude's 4. That's good. All right, so now we know y equals 4 sine omega x. Still got to fill in something, though, for that omega. All right, looking at the graph, we see the period of the graph is, okay, it is 8 pi. I heard some other things, though. So we better look at why it's 8 pi. Why is the period of the graph 8 pi? How far out does this graph go before it repeats itself? That's what we're looking at, right? So when you start there at the origin, I'm going to follow it up here with the cursor, okay? I'm starting at the origin, going up, coming down through halfway, going back up. That's how far I'm going before I repeat. So I look at the scale on my graph. This is how it was labeled in the textbook, 2 pi. The next one must have been 4 pi. They didn't have this labeled, but let's put it 6 pi. 8 pi is how far out this graph is going before it repeats. Are we seeing that a little better? If you didn't see it before, you're seeing it now. Period's 8 pi. 8 pi, though, is not omega. That's not what goes in place of that. What did we know about the period? Period is equal to, what was that formula I told you? 2 pi over omega. But the thing is, these two things have to equal each other then, don't they? We're saying they're both equal to the period. So 2 pi over omega has to equal 8 pi. How do you solve that? Here's a little algebra. Well, first, algebraically, we'd want to get rid of omega in the denominator, so we'll multiply both sides by that so that they cancel there. That will give me 2 pi equals 8 pi omega. Then what would I do? Trying to figure out what omega is. Don't lose sight of what we're trying to do.
You solve for omega.
So how am I going to do that?
Divide 2 pi by 8 pi.
Right, so I'm dividing out this 8 pi so that I get rid of that. So I've got to divide over here by 8 pi. So omega must equal what? 1/4. Good. So my equation here then, coming back to remember my job is write an equation. So y equals what? 4 sine 1/4 x. That 1/4 x part's the argument of the trig function there. I'm trying to put it in parentheses to kind of separate it for you. Sometimes they'll put it in parentheses and sometimes they won't. I think it's a little clearer maybe too, but sometimes the textbook does, sometimes it doesn't. That was a little bit more work maybe to go backwards. Finding the amplitude wasn't bad, finding the period wasn't bad, but then we had to figure out what that omega value was by setting 2 pi over omega equal to the period that we found there. Questions on this part? Anybody got lost in that part there? Okay. All right, so I want to take a minute and look at what the other graphs look like, just so you would be familiar with overall how we're getting those, what they're looking like. I'm not going to plot point by point, but there's some things about those graphs I want you to know. I want you to know basically what the secant, cosecant, tangent, and cotangent graphs look like in general. I want us to think about where these graphs are undefined and just their general overall shapes. So let's look at those just a minute, see how many we can get through. We're going to start out, I don't remember what the textbook starts out with. This is in section 6.5. But we are going to start out with y equals cosecant x, the graph of that one. Okay. Because I want you to recall that cosecant is the reciprocal of which function? The sine. We know that the cosecant is equal to 1 over the sine x. So therefore now we see that when the sine is equal to 0, what does that do to my cosecant? Right, it's undefined. So if the sine of x equals 0, cosecant of x is undefined. That means in these graphs, in all these others that have things in their denominators because they're reciprocals of other trig functions, we're going to have some places that are undefined. How do I illustrate undefined parts of graphs? How are those usually illustrated in graphing?
It's an open circle, isn't it?
I might have an open circle, a hole in a graph. That's one way that I show where a point is undefined. What else? What about when I put those dashed vertical lines in? What are those called? Anybody Anybody know what those things are called? Well, we'll see them here in a minute. We'll talk about them then. All right, so where does the sine equal 0? Remember when we talked about the x-intercepts on the sine graph? That's where the sine's equal to 0. Where does the sine equal 0? It's when your y-coordinate's 0, right? So where was that?
It's your whole number integers of pi.
Okay, so at those integral multiples of pi. So that means then that the y equals cosecant x is undefined at integral multiples of pi. If sine x is equal to 0 at integral multiples of pi, then the cosecant's going to be undefined at integral multiples of pi. Let me draw a graph over here. Here's how we sketch a graph of cosecant. To sketch a cosecant graph, you first draw the corresponding sine graph. That sounds a little strange, but first we're going to sketch up what we know, the sine graph. Sine goes from -1 to 1. I've already put a graph of sine up here before, but let's illustrate it here. I'm marking off those same values that we plotted at the end of Tuesday's class. We're going to draw in the sine graph here. So y equals sine x will be in black ink. It's going to look like this. Oops. Okay, so here's what I did. First sketch, we'll say sketch, y equals sine x. The cosecant graph is going to be drawn off the curves of the sine graph. Okay, that's what it's going to look like. So this graph here is not really part of my graph for cosecant. It's just going to be helping me. So I'm going to kind of blot out part of it just so I can use it as a guide. I can use it as a guide anyway, but I want to stress that what I just drew up here in black is not part of the cosecant graph. It is only helping me draw the cosecant graph up here. Because what the cosecant graph is going to do, and I'll put it up here in blue, it is going to be parabolas, basically, they look like parabolas, off of the curves of the sine graph. Everywhere there's a curve, it's going to be like this. Now, what's happening is you'll notice I've left up here where we've crossed through the x-axis. Remember, those were the x-intercepts for the sine graph, but that's where, and I'll have to use a different color here, that is where the cosecant graph is undefined, in between these places. See right there? In between these parabolas I drew up. It's a very disconnected graph. The cosecant graph is going to be this, all those U-shapes that we're putting on there all over the place. That is the cosecant graph. That's why I say if you have something like y equals cosecant 4x, first draw the graph for y equals sine 4x, the one we've already talked about. That's why we spend a little bit more time talking about the cosine and the sine than what we will these other four, because they're going to be the basis for your cosecant and secant at least. All right, so I really should take out all that black part. I'm leaving it there for now so that you can see that's where this stuff came from. I could still plot values. I know that the sine of pi halves is 1. Cosecant's the reciprocal, it's also 1. That's my point right there at 1, 1. I could plot these others. They're not pretty points to plot, but we could do that. But this is our sketch. I want you to know that the cosecant graph is drawn off the curves of the sine graph. The cosecant graph is undefined at the integral multiples of pi. These dashed vertical lines I put through here are called asymptotes. So we've got asymptotes in between these U shapes. Asymptotes designate places where the graph is undefined. This graph is discontinuous. It is not connected. I have to lift my pencil to draw it. The sine and the cosine were nice and continuous and connected graphs, weren't they? They just were very smoothly drawn. So what do you think is going to happen with the secant graph? This was cosecant. What do you think I would do to draw the secant?
You'd do the same for cosine.
I'll draw the cosine and do the same thing. That's right. So y equals secant x. First, sketch y equals cosine x. I'll put y equals cosine x in blue this time. Oh, I need to put my x coordinates down here. And then we would draw off the curves here in black. I'll put the actual y equals secant x. Now these vertical asymptotes are never crossed by these U shapes. They get very close. That does not look too vertical, but bear with me there, okay? These U shapes, they are continuing on upward and downward, but they get very close to the asymptotes. They do not cross them because the graph is actually undefined where the asymptotes are coming down through. Since secant x equals 1 over cosine x, the graph of y equals secant x is undefined when cosine x equals 0, which happens at odd multiples of pi halves. That's where that stuff's happening, odd multiples of the pi halves. We see it where we have the asymptotes. That's where this graph is undefined. I want you to have an idea of the basic shape of what secant and cosecant would look like, how they're formed off the reciprocal graphs of sine or cosine, and we need to be thinking about where they're undefined. Do you have to memorize that? Well, not really. If you know that secant is 1 over the cosine, just think about wherever the cosine's 0, then that's where your secant's undefined. Does that make sense what I'm saying on that part? For the cosine 0, that's where the secant will be undefined. Okay. Let's see what we've got over here on this part. All right. We still need to look at tangent and cotangent, but I want to kind of leave you today with secant and cosecant because they relate so much to that sine and cosine. So whatever your graph is, whatever your equation says with secant or cosecant, first change it to whichever the reciprocal is. You know, if it's secant, change it to cosine where it says secant. Graph that and then graph off of those curves like we're looking at here. I'm going to ask you to look at some practice problems over the weekend. Okay, plus you're studying your unit circle to make sure you've got that down for Tuesday for a quiz in class on Tuesday. Some of you missed that. Some of you came in late, missed that part. So let me go back over here just a moment. First, let me give you some practice problems, okay, before I forget that. In 6-4, it would be an excellent idea on page 404 to practice with numbers 11 through 29 odd and 35 to 71 odd. That's all with sines and cosines and their graphs, amplitudes, periods, writing equations for sines and cosines based on what you see or if they tell you the amplitude and period. In 6-5, I think you can do a few of these with cosecant and secants. I didn't pick out the exact ones yet, so let's look at, I had them picked out, but I didn't go that far. So 4, 5, 4, 5, 13, 14. Oh, I missed some here. Sorry. Let's change that up a little bit. 4, 5. We are going to get 13 and 14, but there were some before that I missed somehow. Okay. 4, 5, 9, 10, 11, 12. Well, we could have said something through something there. Yeah, 9 through 14 works. It's just because I'm checking them individually here. 9 through 14 works for that part. And then let's go down. See, it's got the cotangent and tangents mixed in, and that's what I'm trying to not hit right now since we did not talk about those yet. 25 and 27. We'll just leave that at that. That looks like a little more than usual maybe, but practice with those. Study the unit circle. Let me go back here just a moment in case you came in late today. Where was that? Tuesday. We're having a quiz on the unit circle. It'll be just like the blank unit circle you have on D2L. Okay, but you'll do it in class on Tuesday and then turn it in. Okay, is everybody clear on that? Tuesday, September 23rd, a week past Tuesday, we'll have our first test on Chapter 6. Just want to make sure everybody's getting the information here. Anybody have a question? All right, then you all have a great day.